Okay, good morning, everybody. So thank you for joining us for this week's Combustion Webinar. It's our great pleasure to have Dr. Atakan this week to deliver a webinar for us. Dr. Atakan is currently a full professor for thermodynamics and a chair of engineering thermodynamics, Department of Mechanical and Process Engineering at the University of Duisburg-Essen. He received his diploma in chemistry and a PhD in 1992, both from University of Heidelberg. Before he joined the University of Duisburg-Essen, he was a research scientist at DLR and Bielefeld University, and obtained his habilitation in physical chemistry in 2000. He is a fellow of the Combustion Institute. He is in the editorial board of the energy section of Applied Science and was in the editorial board of Open Journal of Thermodynamics. So let's welcome Dr. Atakan this way. Thank you.
Thank you very much for this nice introduction and also for the invitation, also to Katharina and Yiguan. Okay, today I'd like to talk about engines and polygeneration. And it's not only about my own work, but also about the work of our DFG research unit. And I will introduce the work of the colleagues while we are coming to their work. Let's starting with a few things you already know, I assume. I think we all know that we have some problems with the fossil fuels, that they are rare, that they lead to carbon dioxide emissions, and we have the problems with the climate change we'd like to, reduce this carbon dioxide emissions. So due to this, I think not only in Germany, but worldwide, we are going towards solar and wind energy, with the well-known problems that they are not aligned to the demand. And so due to this, flexible energy conversion is getting more and more important. And at the same time, we have quite some demand for energy storage, mainly with high energy density. And if you regard just such a slide where you look for the time you can store energy and for the power you can get out of, you would end up generally with some, chemical compounds if you want to store, like synthetic fuels, biomass, hydrogen, hydrocarbons, ammonia, but also hydroelectric. And on the other side, it seems to be quite clear that natural gas will be used for quite a while, at least in the midterm, at least according to the German academies. They say that we will continue using it until the carbon dioxide reduction gets higher than 80% approximately. And so due to this, we started thinking together with several colleagues from thermodynamics, mainly with all the thermodynamics professors, we were sitting together and thinking, okay, what kind of solutions could we find, for example, to help in the energy transition? And we're thinking about the usage of natural gas. Can we do this perhaps in the more rational way? And one of the things, if you regard methane usage or natural gas usage nowadays, then you'll see that around 95% is used for energy conversion, while the remaining 5% are used in chemical industry, generally first to produce syngas, and out of syngas you can make methanol, dimethyl ethers, or you can end up with ethylene and then some polymers or so. And the question is, could we have processes where we produce both of those together, some work output and some chemicals output, and perhaps also some heat output? Could we have some holistic conversion of species and energy? And somehow we have to assess it, because the main question is also, is it really better than two separate processes? And for this, coming from thermodynamics, one of the things is, okay, we can look for entropy production, try to reduce it as far as possible, or in other words, reducing the Exergy losses. Or on the other side, we could also look for some economic assessment. Will the prices perhaps be lower than in two separate processes? And since we're coming from combustion, first of all, let's look at methane conversion. And if we start reducing the amount of oxygen added, we can, for example, go to an equivalence ratio of 2. So the amount of oxygen is only half as much as you would need for stoichiometric combustion. Then you would end up with synthesis gas and some water. But what's more important at the moment is you have also some negative Gibbs energy, which is quite high. And in principle, you could do some partial oxidation, producing syngas, and at the same time, also having some work output. And this is generally not used. You can call it wasted. Similarly, you can continue reducing the oxygen further towards an equivalence ratio of 4. You can even get more hydrogen out. Surely the possibility to transfer some work will be reduced, but nevertheless, it's not zero, and it may be reasonable also to use this, that you can have some work output. So again, this would be a polygeneration process with at least 2 or even 3 products if we also have some work, some heat which is transferred. If you go further, you can just leave out the oxygen and then think about some exergonic and exothermal reactions, for example, towards acetylene and hydrogen. It may also be benzene and hydrogen. And for this, you would have to add some work. And this would be a typical process where one could think about storing energy. So you could add this 156 kilojoule if it would be reversible and produce acetylene hydrogen, either use it directly here in chemical industry, or if you don't want to use it there, at least you could burn it again and you would have a higher heating value. Or this is one process which is mainly investigated by Olaf Deutschmann and his colleagues. We could also go for dry, where we could convert carbon dioxide with methane towards syngas. And again, we could store energy because, again, the Gibbs energy is highly positive. And again, we could think about, could we perform it with what we know from combustion? With respect to Exergy, I've always this slide because at least the chemists in the combustion community normally don't know much about it. Exergy is just the available part of the energy, and it's depending on the actual state of a system and on the environment. So it's mainly how much energy is convertible in any other form of energy if you bring it into equilibrium reversibly with the environment. And Exergy can be lost or destructed due to irreversible reactions, due to heat losses, or due to mixing. And it can easily be calculated from thermodynamics, just looking at the irreversible entropy production and the temperature of the surrounding. And the main idea is now we have lots of available energy in our fuel or in our precursor. And now we want to transfer as much as possible to work or to the exergy of our useful products, which would normally be in the exhaust gases. And we want to reduce the exergy losses as far as possible. And in principle, these kind of polygeneration processes were already investigated by several groups, but generally, as it's shown here from one paper, they are combining 2 well-known processes. For example, here, some iron production process is used where you add some iron ore and coal and end up with some hot iron. But since you're producing carbon monoxide, you can use this again, for example, in a combined cycle and produce heat and electricity together with the metal. You will also have to add some natural gas in addition to the carbon monoxide, while the processes remain unchanged here. In our case, we want to look into the process and have one single process which is modified, and we want to use them for polygeneration. And since we're coming from combustion, we ended up putting those 2 things together into a single engine. And generally, you will be asking yourself, why an engine? My first paper about this topic, I was writing about gas turbines, but they are quite expensive. And nobody wanted to give me his gas turbine for doing some experiments under very fuel-rich conditions. Instead, with engines, we know at least that they are industrially approved. They are relatively cheap. And if you have the HCCI process, so meaning you have a homogeneous charge, so pre-mixed mixture, and you ignite it due to compression, you have a mainly kinetically controlled process. Generally, there are also always some questions why HCCI. I'll come back to that in a minute. The other thing is we don't only have the compression where we heat it up, but we have also the expansion directly after. And if the product would tend to react further, you can stop them due to cooling in the expansion. That's again, at least sometimes quite helpful. And so the idea is for flexible energy conversion, we may have such a knob, and we can choose, for example, if the demand would be energy storage, we could add some work and some methane or natural gas and end up with hydrogen, benzene, acetylene, and whatever comes out. Or if the demand is changing, we could end up with, so we would now need some electrical energy and chemicals. We would instead add some oxygen instead of the work and end up with some work output and with some syngas. But we have some problems with the natural gas or with the methane because it is relatively inert. And so due to this, we need something as an additive quite often to have some ignition of this mixture. And for example, things like DME, dimethyl ether, are used, which is not really wanted because out of syngas, you're producing dimethyl ether, so you don't want to add too much of it. Or recently, we are also looking at things like ozone, which can be added to help with the ignition. So our approach here is we want to use engines directly for the conversion of species and energy. And we want to use the knowledge of the combustion community. We want to go along high temperature paths, so we will not be able to produce things which are very unstable at high temperatures. But we want also to use all the mechanisms which were developed within the combustion community generally in order to reduce the amount of pollutants. Now, our aim is not to reduce the pollutants because something like carbon monoxide would be normally a pollutant. Now we want to maximize them using these kind of mechanisms and all the other techniques we learned in combustion. And so we want to go away from the pollutants towards useful chemicals and investigate the fundamentals of such processes. And with respect to the engine process, I often get the question, why don't you want to use spark ignition? Why do you want to use HCCI processes? Because many of you will know that HCCI processes are difficult to control mainly in the lean regime. But you should keep in mind that we generally have to go to quite fuel-rich conditions. And if you want to ignite with spark ignition, the flame propagation depends on the turbulent flame speed. Turbulent flame speed, again, depends on laminar flame speed. And this is dropping strongly if you go towards high equivalence ratios. And so due to this, with HCCI, we think, and we also proved, that it works better. And I'll show you also a few slides about that. So in total, the HCCI process is more or less an Otto cycle. So if we start at the bottom dead center, we have the compression, then a more or less isochoric ignition, then the adiabatic expansion, and then you would have the exhausting afterwards. And therefore, for the exhaust, we're interested to use what's coming out there at that point. And our main goals here are to answer such questions as, are high yields and high selectivities possible in engines towards synthesis gas, but perhaps also towards unsaturated or partially oxidized hydrocarbons? Is it easily possible to control such a process that you either add work or remove work depending on the needs? And also, are there, that's perhaps the crucial question, are there any advantages compared to separate processes with respect to total energy and exergy balances or with respect to the economy? And with respect to piston engines, one should keep in mind that it also leads to several couplings which one has to care about. First of all, if we just look at the energy balance, the amount of work transferred is just the amount of change in internal energy and the heat transferred. Let's think about some adiabatic compression. Then it's clear that the compression depends on the final temperature depends on the compression ratio and can be calculated according to this formula if Cp would be constant. But here are some calculations with non-constant Cp. But what's important is if we increase the compression ratio for different mixtures, for pure methane, for methane with oxygen 1:1, or methane with air, you see that the temperature rise is not bad, but if you regard the ignition temperatures, which are around 1300 K, if you want to have the ignition in the milliseconds regime, then we are far from it. With oxygen, it's getting better. With air, it's getting even better, but you should also see that we have here compression ratios of 40, something like 20 would be more realistic. While if we start heating the mixture first, a little bit towards 450 K, things are looking much better, but not perfectly good. So there's something to be done about that. So to really end up with some ignition. The other thing one has to keep in mind is we want to go for fuel-rich mixtures. And so we have to care about soot formation. You may know this famous diagram by John Deck. And it shows you the regime of the normal HCCI, where you don't have too much NOx production and no soot formation. And we want to go for somewhere in this corner where we have high equivalence ratios, but we shouldn't have too high temperatures at the end, because if the temperature would get, at least in some regime, too high, we would end up with lots of soot at the end. And so we went through a procedure. So we are running this project now for 8 years with 8 projects. First of all, we have some a priori evaluation. So first of all, we think about, is the thermodynamics favorable in principle? Is the predicted kinetics fast enough to have such a process in the engine, using first of all non-validated mechanisms? And what could be probably favorable conditions before we start doing experiments also with respect to the kinetics, using shock tubes, rapid compression machines, or flow reactors, and later on also in engines. A good idea is to start with something relatively simple, and a single zone model with detailed kinetics is a good starting point, including some heat transfer using the Washner equation. And so we have such a system. We use a reaction mechanism which is already established. You will find the reference here. And we start with some initial conditions, and then we go along the crank angles or along the changes in volume, calculate with the kinetics and thermodynamics the changes in temperature, pressure, and composition. And we do this time step by time step, as many of you will know. And then at a certain point, we get ignition, but we are mainly interested now, first of all, in integration of the work, but we want to know also what's coming out at the end with respect to the product gases, with respect to Exergy and the work output. And if we have just a typical cycle this was calculated by Dominik Schröder, who changed his name to Freund now, and by Robert Hegner, at equivalence ratios of 2, a relatively low engine speed, compression ratio of 18, and 428 K. And it's already the 10th cycle, because it always helps you to have some residual gas at higher temperatures for the ignition in this next cycle. And after a while, you will end up with a steady state process. And if you now regard the products here after ignition, you see that we end up with reasonable amounts of hydrogen something like 18%, or carbon monoxide, something around 13–14%. In the exhaust gases, while, for example, ethylene or acetylene are only produced here under these conditions around the ignition, but afterwards they are reduced near to zero. Now, the main point for the initial investigation was also how can we reduce the intake temperatures, because our experimentalists did not want to have higher temperatures than around 150–160 centigrade approximately. And if you look for an engine with a compression ratio of 16 and a speed of 3,000 per minute, having neat methane, you see that we'll need quite high intake temperatures for ignition if we go for high equivalence ratios. You can reduce it, for example, by increasing the compression ratio. That helps a lot. What also helps is reducing the engine speed, or what's perhaps best, mainly under very fuel-rich conditions, is adding an additive like dimethyl ether, something like 5 up to 10% seemed to be reasonable. And this was also one approach we were using afterwards. What is predicted, at least from the modeling, what should be coming out? At equivalence ratios around 2 to 2.5, we should have lots of hydrogen coming out, lots of carbon monoxide coming out, so synthesis gas. We can also change the ratio between both, which is sometimes quite important. While if you want to go for acetylene or ethylene production, you will have to go to very fuel-rich conditions. And surely the amount is not too high, but you should also keep in mind that we are doing all these things with air as the oxidant. So we have relatively high amounts of nitrogen in the mixture. But since it's quite tedious to do all these by some guessing what may be good conditions, we have colleagues, mainly Olaf Deutschmann and Henrik Goslar, who do this with mathematical optimization. And in these calculations, they went for an optimization of ethylene. And so for each temperature here, they had one optimization restricting the amount of DME and the engine speed to some maximum values. And as you see here, for example, if the intake temperature is not too high, you would have to add around 7% dimethyl ether. This was, well, their limit. While at the higher temperatures, you would go for higher engine speeds. What's perhaps most interesting is how much ethylene is predicted. And you see something between 15 and more than 20% seems to be possible. And the equivalence ratios, which are also optimized, would then be somewhere between 3 and 4, which is a dangerous regime with respect to soot formation, to be honest. Okay, this is about the first evaluation. The next thing is we should validate these things in experiments, because most of the models we're using initially were not really validated too much for these kind of conditions. So we have different experiments using shock tubes in the group of Mustafa Fikrian and Christoph Schulz. We have flow reactors, mainly Tina Kaspar is working on this together with myself. And we have a rapid compression machine, which is more or less the first step towards the engine. And this is done by Robert Schiesel and Ulrich Maas. And at the end, we also developed a relatively small model, again, in the group of Ulrich Maas. And so if you look for a few exemplary results from the shock tube, where you can have relatively high temperatures at small time scales, but also relatively high pressures, you see that the ignition delay times can be shifted from neat methane, this is this curve here, or these points here, by adding different additives. And here you see DMM, dimethyl ether, diethyl ether, or N-heptane as additives. And it doesn't really matter which of those additives you're using. If you want to end up, let's say, with 1 millisecond of ignition delay time, or 1 or 2 milliseconds, then you have a shift of around, let's say, 150 to 200 K, with nearly any of those additives added with 5 to 2% of them. And with respect to the mechanisms, I should admit that this was the Polymec coming from Ulrich Maaß and Silvia Porras, which is at that point slightly worse, this calculation for DME, compared to the Berkey mechanism. But nevertheless, at least additives seem to be helpful. Another question we got quite often, or we get quite often, is in natural gas there is also ethane and propane. Couldn't this help already? So perhaps we don't need any other additive. And some of the experiments were done by Dennis Kaczmarek together with Tina Kasper in a simple plug flow reactor. Here you're mainly seeing the isolation. In the middle of it, there's just a quartz tube. And at the end, we normally have some mass spectrometer or some gas chromatograph for the analysis. The time scales are now much larger, something like 10 seconds. The temperatures are lower. Now we can go up for 1400 K, but these are in the old reactor with 970 K, and pressures could go up to 20 bar here. And since we are only looking at the final products, the main question is at which temperature is methane really converted? For methane, for neat methane, it's somewhere around 800 K, while if you have ethane and propane added in total by 10%, you see that it helps a little bit, but not too much. While, for example, for N-heptane, we can even start at around 600 K, and for dimethyl ether, it's quite similar. It's starting much earlier. So again, we are going towards such additives like dimethyl ether or N-heptane. And so Dennis Kaczmarek made a nice map of what is coming out for different equivalence ratios and for different temperatures. For example, the syngas is mainly at not too high equivalence ratios and relatively high temperatures, while the oxygenated species are mainly produced at relatively low temperatures. Ethylene and acetylene can be produced at high equivalence ratios and relatively high temperatures. I won't go through all the numbers, but some of them are quite high, like 9% ethylene, for example. Another question we also get quite often is, can we really end up with reasonable amounts of ethylene also in some engine-like process? And we looked for this in a rapid compression machine. This was mainly done by Mark Werler, Robert Schiesel, and Ulrich Maaß. And here you see experiments for quite different equivalence ratios between 1 and 15. And for example, for ethylene, you see that at least at equivalence ratios of 6 to 7, you can end up in a non-optimized process with around 2% yield of ethylene. So at least for non-optimized system, it doesn't look too bad, but under some of these conditions, we always have the danger of soot formation. Okay, then the next step is going towards engine experiments, because in real engines, several things are more difficult than in our nice kinetics experiments. And this is mainly done by Sebastian Kaiser and Kai Banke, and earlier by Sebastian Wiemann. And it's an engine which, it's a quite simple scheme here. I think I will not go through the details, but we have the pressure measurement inside. We can go for intake temperatures of 150 to 160 centigrade. Initially, the compression ratio was restricted to 10. Now we can go for 20. And most of the experiments were done at relatively low engine speed. The displacement volume is 0.3 liter. And at the end, we have some exhaust gas analyzer and some smoke meter. And you should also keep in mind that the laboratory equipment has to be changed a little bit, because our exhaust gases, when mixed with air, are ignitable again. So due to this, one has to take care about that. And if you look at the engine, it doesn't look too modern, but nevertheless, it's quite robust. And here's also the gas analytics. And this was the engine used most of the time. It's called a BASF octane engine. And In the very first experiments, we started with spark ignition because we already had the setup for the spark ignition. And we also did the one-zone modeling. You see all the co-authors at the top. The experiments were done by Kai Banke in the group of Sebastian Kaiser. And what you see, we are comparing here now the experimental results with the modeling. The main parameter is the equivalence ratio. And what you see, okay, if equivalence ratio is 1, we end up with carbon dioxide mainly, while hydrogen and carbon monoxide, those two, are mainly produced if you go to higher equivalence ratios. But starting at an equivalence ratio of 1.5, we get more and more misfires, while the model doesn't care about. We model the spark by some OH addition at the top dead center. While in the engine, you see that you don't get much output in the average. And if you now look at the efficiencies, at the exergetic efficiency and at the thermal efficiency, surely thermal efficiency drops because the more fuel rich you get, the less do you convert towards carbon dioxide. While if you look at the exergetic efficiency, you have lots of the exergy in the products together with the work output. And so at that point, we can increase the efficiency from around 40% to around more than 60%. While these points are misleading because if you don't have ignition, you end up with doing nothing. And if you conserve your methane, surely you don't produce any entropy, but this is not really what you want. So even if you conserve all the exergy which is in your fuel, this is not what's wanted here. So this may be also misleading at that point. Now then, the colleagues did lots of nice experiments, now not only in SI mode, but also in HCCI mode with dimethyl ether or with diethyl ether added. And here you see the regime of equivalence ratios from 0.5 going up to around 12. There are lots of data. I will not go through all of them. But what you see is with HCCI, we can easily end up with syngas, for example, at equivalence ratios around 2 with quite high amounts. But we also have to care about soot. You see the amount of soot is also increasing here. So you have to find a compromise around here if you don't want to have too much sooting. The next problem we have also to care about, I'll come to this back in the next slide. Under certain conditions, we have a problem with how often do we get misfires. So this coefficient of variance is one parameter which should not be too high. But regarding now the exergetic efficiencies, you see that we can go up to 80% here with DME and even slightly higher with diethyl ether. And the nice thing about this diethyl ether experiments, which are at very high equivalence ratios, that the amount of soot is reduced quite strongly. So if you go for very high equivalence ratios, then this helps. But there's another problem I didn't address so far, or not too much. In these experiments, we have around 10% additive inside. This means that around 15 to 20% of the energy is coming from the additive. And as I told you initially, things like dimethyl ether are produced out of syngas. So this is not wanted. And one part of our research is now going in the direction to avoid at least these ethers as additives. But let's also go through the other things we learn with doing such engine experiments. For example, Kai Banke always uses these kind of experiments where he adds more and more dimethyl ether while holding all the other gas flows constant, now here for an equivalence ratio of 1.75. And what he sees is initially here the coefficient of variance, it's this one. It's on the right-hand side, on the right axis. It's quite high initially. So it means you have lots of misfires. While it's reduced here in this experiment at dimethyl ether mole fractions of between 9 and 10%, relative to methane. While if you add further dimethyl ether towards 11%, for example, the pressure rise rate is getting quite high. And this is a problem which is known also from lean HCCI processes. The pressure rise rate shouldn't be too high because you're in danger of destroying your engine. So here in the middle, we have a window where we can go for this process nicely, but we should neither have too small amounts of dimethyl ether nor too high amounts in order to have a stable process. If you then regard the selectivities, again, a comparison of experiment and our single zone model, we have also multi-zone model results, but these are much faster. They are in reasonably good agreement. And so we can have lots of predictions also with such relatively simple models, and also the amount of hydrogen carbon monoxide are relatively good. And we can also vary the amount of hydrogen to carbon monoxide, which is also interesting sometimes. With respect to the exergetic efficiencies, as I already told you, we can go up to 80%, while the thermal efficiencies are not very high. It's around 10%, but nevertheless, around 10% of the energy is converted to work, while the remaining part is found in the chemicals or as heat. So now if we compare with separate conversions, you see, for example, from the literature, we found the best HCCI process has something like an exergetic efficiency of 48%, which is only towards work, while the best syngas production process end up with 63% exergetic efficiency from the literature, while what we found here is something like 80%. So it seems to be promising at least. But the next question is it also economically favorable? And we are not yet finished, because here we end up with a mixture of different gases. And we have also to think about how much does it cost us in terms of exergy to separate those gases. And so due to this, we went for a process for hydrogen production together with work and heat, and also assessed the separation together, and then the economic assessment. And so we end up in theory, so it's only a modeling study, with such a process where we start here with our methane and air, have our engine or single zone engine model. We have a preheating here. Then we have some exhaust gas recirculation, and this is varied later on. The carbon monoxide is converted in a water gas shift reaction towards hydrogen, and then we have a membrane in our model made out of palladium that's quite expensive. And then here the hydrogen is separated, and then we also need some pumps or compressors to end up with a reasonable pressure of the hydrogen. If we go through such a process, we have to analyze each part here with respect also to the economics. So we have some exergy flow rates for each compound. So we are comparing how much cost rates are getting into a process from the fuel, how much are getting out, what's the difference? What's the difference for the products? How much do I need for the investments for operation and maintenance? And how much does it cost us to destroy exergy or to lose exergy? And so for this, we have these cost rates. So each exergy flow rate has to be multiplied with the cost per exergy. We get the cost rates. Then we have a cost balance for such a system. So we're just comparing the difference in the cost of fuels and the investments with those of the products and the losses and destruction. We compare the exergetic efficiency, so how much is lost compared to the exergies initially provided. And the exergo-economic factor is perhaps also quite interesting. It's comparing how much does the do the investments and investment costs contribute to the costs, and how much are the total costs resulting from the investments and from the destruction of Exergy. So if this is around 1, you should look for processes which are cheaper with respect to investment. If this is near to 0, you should look for thermodynamically more favorable processes. And I will not go through this one. So let's look for the product cost rates of hydrogen, but also of electricity and steam and water. And what we're seeing here is if the exhaust gas recirculation ratio is not too high, then we have relatively high product cost rates here for the hydrogen. And what's perhaps most interesting, 67 to 80% of the costs are coming from the hydrogen. This means 30 to 20% are coming from the electricity and the heat. So it's worth also looking at those two while you're looking at the hydrogen. So since 20 to 30% of the costs of the earnings are coming also from the other products. If you look for the hydrogen costs per kilogram, and this is our typical market price we could find. So if you can compare our process here. So if the exhaust gas recirculation ratio is not too high, then we are at the lower limit, and it seems to be quite reasonable to have such a process. So it's competitive. Then the next question is, we are doing this economic assessment, and from somebody coming from thermodynamics, we are never quite sure about what can we believe these numbers or not. And so we did also some sensitivity analysis, some global sensitivity analysis for low and high exhaust gas recirculation ratios. And what comes out is, first of all, that the total sensitivities are looking the same for both cases. And there's only one thermodynamically important parameter which is really sensitive, and that's mainly the investment costs of the hydrogen membrane, while these, like interest rates, lifetimes, operating hours, are not as easy to be influenced from our side. So it may be reasonable to look for processes for separation of hydrogen which are not using as expensive membranes as we were looking at. And this work was done together with Ali Güngör from Ege University in Turkey. So the total exergetic efficiency, with including all the separation processes, dropped from 80% to 60%, but nevertheless, it's looking quite promising at the end. If you're looking now for the Exergy destruction rate, there's one which is most important, that's the engine, unfortunately, while the others are not as important, like the water gas shift reactor or the hydrogen membrane. And with respect to the exergetic efficiency, the water gas shift reactor has a relatively low efficiency, but it's not as important at the end, while the exergetic efficiency of the engine is again relatively high. So these things are looking quite good. And with respect to the exergo-economic factor I was introducing before, we see that for most of them, it's worth looking for process where the investments are lower. So for example, also scaling towards larger engines should help at that point. Okay, let me come to two more very brief points. One thing is, let's look for a few experiments where we replace the ethers with ozone. And this was also due to, yes, where we found some work about ozone addition in normal HCCI engines for fuel-lean conditions. We're thinking, can we also use it for fuel-rich conditions? And in one discussion with Sigwan, we were also thinking about what's the mechanism of it. But first of all, let's look at some engine results. And here, Kai Banke was doing some experiments where he was replacing DME by ozone. And by adding, for example, 70 ppm ozone and increasing the inlet temperature, he could reduce the addition of DME towards zero, while even he could reduce the addition of ozone towards zero if he would go, or if he's going for high enough temperature. So we could even get rid of all the additives if we go for high temperatures at high compression ratios here, 18.5. But in general, the engine people are quite happy if they have something like ozone for controlling the process. Okay, but if you're looking now at the amount of the power needed compared to the power converted in the engine, we need around 6% of the power initially, and this is reduced towards 0% if we don't add any ozone. And we also modeled this here, and here are the experiments of how much ozone is needed to replace DME. So if you go to lower DME, you need more ozone. And this is what we modeled with the Berkeley mechanism, which is not optimized for these conditions, so it's not perfectly fair, while the Polymech did a slightly better job here. While we are not exactly sure about the experiments, because we also saw that some of the ozone may be destroyed in the entrance tract of the engine. So due to this, perhaps even we have to reduce those values, but nevertheless, we can reduce the DME amount quite reasonably and reduce for this single condition, for example, the amount of energy added from 17 to around 11%. And perhaps one slide, you may see more of this at the combustion symposium. How does ozone help us at that point? If you look at the conversion of methane, you see that ozone is destroyed much earlier in the engine. So there's no ozone when the methane is mainly reacting left. What's happening? Surely OH is also reacting quite fast, while there are several buffer molecules, and one of the most important is the methyl hydroperoxide, which is produced in between. And then after this, hydrogen peroxide and formaldehyde are produced, and these are really helping for the ignition at the end. Okay, now. We present this at the upcoming combustion symposium, so if you want to hear more about this, also about the flow analysis and these kind of things, just have a look at this talk. Another topic I will not come to today is about energy storage, because we can also add energy and convert things like methane or methane-ethane mixtures. This is mainly the work of Charlotte Rudolph. And I may also say, so you may read more about this here, but if you're interested in these topics of energy storage, either chemically or thermally, perhaps I may also invite you to the Hereo seminar we will have in March. It's a relatively small seminar with around 60 to maximum 100 participants, where we want to discuss in detail such topics about what can we contribute to also chemical energy storage and what research needs are present there. Okay, and if you want to learn more about the things I was telling you today, you may read also the recent review article we published last year, at the end of last year, with all of our co-authors. I won't read them now once again, but perhaps a final question, which we again got asked by one of the reviewers. How about scaling such an engine process to industrial scales? Is this realistic? And if you look for normal syngas production in industry, they produce around 100,000 cubic meter per hour of syngas under standard conditions. And if we now do some rough estimation with a 100-liter engine, meaning the displacement volume, as they are used for cogeneration, and extrapolation from our work with a much tinier engine, we would estimate that you need around 37 engines to produce this amount of syngas. So is this realistic? I think it could work out. Let me conclude. I think the methods of combustion science are quite useful also for quite different energy conversion processes, for example, for polygeneration, but also for energy storage or dry reforming, for example, of carbon dioxide, as it's done by Olaf Deutschmann and co-workers. What's important from my point of view is one should always also evaluate the exergy flows and not only look at the amount of conversion of seven species, because you get a much deeper understanding and a better assessment of such processes. One should also go for the economics, even if we are not too familiar with this. And what we didn't start yet, but what's also important, I think, is looking at things like life cycle assessment. These shouldn't be neglected. But I think at the end, engines for polygeneration have several advantages. And so finally, let me thank the German Science Foundation to finance this multi-PI project now for nearly 8 years, quite generously, and to all the colleagues who contributed at Karlsruhe and at Duisburg. And you may also want to see a few of the faces of the colleagues while we have our workshop always once a year in pre-corona times. Thank you very much.
Okay, thank you so much. So here I received a few questions from the audience and I will ask on their behalf. And the first question is whether you could use hydrogen to enhance the ignition rather than using DME or ozone.
I fear it wouldn't help because hydrogen is also quite difficult to ignite by compression. You need also, again, quite high temperatures. I think we did at least several calculations and it didn't look as if it would be promising.
Thank you.
Sure.
The second question is from Professor Ju. So what is the typical equivalence ratio and the peak temperature? Is it beyond the reach burning limit of flames?
So the reason I ask this question, and Burak, is that seems like that you are operating at a rich condition where that the methane or DME cool flame can work. And that is like my question.
For a cool flame, we didn't care about, but what would be the time scale? So how fast would it be burning?
I would say that probably less than a millisecond.
Then it may be working. So we didn't really look for cool flames, to be honest.
Yeah, okay.
What was the first question? The equivalence ratio. The most of the time we're looking at equivalence ratios of 2 to 3, but as you saw, we went up to 15 or something like this.
So at high pressure, we can see in a reactor about the equivalence ratio of 2. We can see that cool flame chemistry start to kick off.
Yes, it could be working. It may be worth giving it a try.
Okay.
Let's see if we will find the time for this. We're in the final year, but we will have a look perhaps.
Thank you.
Okay, that's interesting. And the following question is from Professor Coates. How do you deal with the probably unavoidable product mixtures? Or can the process be optimized toward single desirable chemicals?
I think Burak gave already a partial answer in the talk, and I asked it before he showed it. So you just have to account for the separation process, but I don't think you will ever have something that is directly usable, probably without purification, is there?
I think so. I think the best way would be if you have a chance to get reasonable amounts of things which are condensable, like benzene. So it may be easy, but quite often you end up with gas mixtures if you go along the high temperature paths, and you will need some separation. I fear I don't see really a chance to end up with a single product, at least not with these kind of reactants.
First of all, I had another in between, which I find quite interesting. So if you had, a surplus available renewable energy that you could convert into chemicals, would such an engine be, flexible enough, 100-liter engine or so, to actually follow the cycle of, let's say, wind turbine field or something?
I think the engine might be flexible enough that this wouldn't be the problem, but we have unfortunately further problems with the energy storage, because if we want to go towards energy storage, we need and as in the beginning I showed the methane slide, the temperature is not high enough. We have to add something like argon to end up with high temperatures. And so if you want to switch within a few minutes, you would also have to change from things like air towards argon. And I think this will be the main difficulty.
Yeah.
So
now
due to this, I feel we are not as flexible as we would like to be.
Yeah. If we go to the final question, which Wenting has already mentioned in terms of a business case, I mean, it's not just a question of, you know, price per liter or price per kilogram. It's also a question of purity, a question of, you know, what kind of thermodynamical conditions will you deliver it at, like, you know, in a gas bottle or so. So have you, in your economic assessment, tried to sort of look at something?
Yes, I think the hydrogen we were producing in the model was at least, I think 3.0 or 4.0, so 99.9 or 99%. And the pressure was also already at high pressure. So due to this, we had the several compressors behind that. So this was already included. But that's an important question. So if you would end up with 90% hydrogen, this may be difficult to find anybody who wants to use it.
Right. So thank you. And I think, you know, I endorse your last slide, and many people coming to discuss that in more detail in the seminar that you mentioned. And maybe this webinar can sort of point towards the upcoming seminar if you give the dates again.
Yes, I'll go back. So here we are.
One question is asking about the effect of lubricating oils on the products. Have you considered such effect?
To be honest, no. I think we are using normal engines, and there is a normal lubricant oil inside, but we didn't really investigate it. So I can't tell you. It seems to be working with the normal lubricant oils, but I can't tell you if they are really important for conversion or whatever.
So the doctor, so the reason I ask this question is like, this is the kind of reactor is different from the common reactor because you have the engine moving around, the piston moving around with the lubricating oil. And it can be a little bit different from the regular, you know, flow reactor or something. That's why I ask it.
Yes, this is correct. But at the end, the lubricant will be mainly at the walls, which are at relatively low temperatures. So the chemistry should mainly take place further away from the walls. So I don't expect to have a really very important influence on the reactions, because we don't see much low temperature chemistry, and often we end up with 5 to 10% unreacting reactants because due to the regions near the wall which are cold, where we don't have the conversion at the end. So this, I don't think that it's too important, but I can't exactly tell you.
The following question, one more question is on the conventional spark ignition operation engine, and it should be able to give much better COV and pressure rising rate than the HCCI, and is more controllable. What is the major disadvantage of SI comparing to HCCI for the present application?
I think the main disadvantage of SI is, I think that there are people who are using spark ignition for similar process. For example, the MIT group by Green and Bromberg are using them. But they have to go to really high temperatures. If I remember correctly, it's something of more than 350 centigrade entrance temperature of the gases. And then at these high temperatures, the flame speed is getting again high enough. But we had problems with our engines to go to these high temperatures. But I think that's the main problem. If you don't have a flame propagation, what do you want to do? So you can only rise temperature of the initial gases. But for this, again, you will need some energy from somewhere.
And the last question is from Matt Cookate. And so have you considered a catalytic partial oxidation as an option to produce a cleaner output stream without soot production?
Yes, we now and then we're discussing this, at least. I'm not sure if you can really call it considered. And I think again, Leslie Bromberg did some experiments also with a piston where he had catalysts on it. I'm not sure if this is really the right way to go, because at the end, then you will end up getting some transport limited process, because always the gases have to reach the catalyst, or you have to need something like, you have something like a porous piston. It can be possible, but it will be, I think, quite different compared to that what we are doing. And quite often, as at least Olaf Deutschmann is telling me, he always likes the catalytic process. People in industry quite often would like to get rid of the catalysts because they're expensive and they are also easily deactivated. And if you would have a totally homogeneous process, at least it may be cheaper at that point and perhaps even more robust. But it could nevertheless be a way to try out. Thank you very much.
You missed the one on the exergetic efficiency. The definition of Exergy efficiency as the professor is defined it.
Do you want to see the slide, or what exactly? I think that there are several deficiencies with respect to this. What we were using generally was all the exergies which are coming out of the engine, meaning the work which is coming out, the heat which are the exergy part of the heat which is coming out, so meaning the heat flow rate times more or less the Carnot factor, and the chemical exergy of the products. So if you would bring them into equilibrium with the environment, and this compared to the chemical exergy of the reactants. So this is what we are using.
Standard temperature pressure?
For the chemical exergies, it was always relatively to environmental temperature and pressure, yes.
And
relative to the environment.
And elemental compounds with zero heat of formation, as we do in combustion.
Yes. The composition of the surrounding was a standard air surrounding, so we didn't look for rocks or these kind of things.
Okay, thank you.
Okay, so let's thank Dr. Atakan again to give us a seminar over the weekend.
Thank you very much for listening.